Hello everyone, my name is Milan Ličina and I'm designer, educator and tech enthusiast. I will be your host for today's presentation, Machine Learning in Real Time, presented by Florent Guine. As a longtime Unity user and a fan, the invitation to announce the first ever Unity talk at CGA Belgrade was a privilege enough. When you add the fact that our guest speaker, Florent Guine, comes from the very heart of Unity Development Lab, this has just excelled to an early Christmas gift. So, for the past few years, we have seen the hype of machine learning and methods for empowering real-time applications. The truth is, there is still a wide gap between research papers and deployed software. Florent had the opportunity to present his work and strategies for implementing artificial neural networks into a game production software via Barracuda. So, this talk comes straight from SIGGRAPH. Florent, please take over the screen as our audience takes notes and prepares for Q&A session.
Thanks, Milan. Hi everyone. So my name is Florent. I'm working on the Barracuda team, which is a part of Unity Lab. So without further add-on, let's look a bit of what we do at Unity Lab. So what is Unity Lab? It's a part of Unity, which is responsible into looking into the future. So we look, it depends on the project, but 5 years ahead maybe. And we have various area of interest. Real-time 3D authoring is one. AI deep learning, obviously. Computer visualization, XR, storytelling, and much more. And in part of lab, I'm part of a team which is called Barracuda. So what is Barracuda? It's an inference library engine. And what does it do? It takes a neural network and make it run inside of your game engine. It's cross-platform, meaning it runs on any platform Unity support, and that's a lot. It's both on CPU and GPU, and we deliver it as a Unity package. The good thing with a Unity package is that its source is available. You just go to GitHub, grab the source, and see everything we do. So it's really good because we have faster iteration time, and you actually see the work happening. So I guess the next question is, why do we do such a thing? And we do it because we have a strong belief that machine learning and real-time 3D together are extremely powerful. They open a lot of different use cases, and we will look at that in that presentation. So let's have a quick look at the agenda. Okay, first we will take a look at various use cases, just an overview of that power of machine learning in a game engine, in a real-time 3D engine. What does it bring? Then we will look at the way we import the model, so from Python to actually running on device. And once you have a neural network running on device, obviously you want it to run as fast as possible. That's going to be the third step, optimization. And in the end, we will look at a practical example. So real-time inference in-game. There's a ton of different network out there, but we can roughly separate them in two broad categories. And that will be medium computational intensity and high computational intensity. There's no low computational intensity in terms of neural network, unfortunately. So medium, they are quite interesting, and it's a category that usually, it's a general thing, it's not always like that, but usually you will have small input size. You might have a network with complex architecture. Which means, for example, a recurrent network. And it might be also a use case where you want immediate feedback, a low latency. And that might be that you actually want the result as fast as possible on CPU. So that those network might be a good fit for CPU, both because they have lower computational intensity and you want less latency. So CPU to CPU. And then we have the other end of the spectrum, which will be high computational intensity. Here we go more toward a GPU because of the sheer raw power of those devices. It might be image-based network, convolution-based network, which usually have large input size. So let's dive a little bit into example about those two categories. So medium computational intensity, we'll look at two examples. The first one is going to be about decision making, agent behavior, and the second one, animation. So what if instead of regular handcrafted uh, AI, you will use reinforcement learning? And actually, you can do that in a game engine, and you can do that in Unity using a package that's built on top of Barracuda, and that's called ML agent for machine learning agent. It's very good, and there's various use cases there. Reinforcement learning applied like that allow two different angles. You could be a game developer, for example, and you want the latest and the greatest of those research papers, but your background is game dev, not machine learning. Then you could use that package, and you will use the best technique out there very easily. On the other hand, you could be a machine learning researcher, and what you want is to try new idea, but you also want fast iteration and an easy environment to test your idea, and then the game engine can provide you that. ML Agent 2.0 was released not so long ago, and it includes a bunch of features to get a bunch of highlights, which are cooperative behavior, variable amount of observation, and also something called task parameterization, which allow to train one network to multiple tasks. Let's move to the second example. So another use cases on medium computational intensity, that's a good fit for CPU probably, will be animation synthesis. So Unity is working on something called ProtoRes or deep pause, depending. And what this is about is to train a neural network to understand what is a natural behavior, natural pose for human, which means if you want, as an animator, you want to have a set of pose or full animation, then it's going to be much easier for you because the network will help you, will maybe flip the ankle a little bit so it look more natural, or twist the head or something like that. And there's a huge potential here. Again, two different use cases. You're an animator, you can just iterate way faster, and it doesn't prevent you to actually fine-tune after that. Or another use case is you're not an animator. Then you can get very good results at a fraction of the time and just cost that will normally have taken. So this is a public paper. If you look for ProtoRes on Google, you will find it. It's ongoing work at Unity. So now, high computational intensity. There's a ton of use cases out there. A bunch: super resolution, style transfer, and everything about XR, so AR, VR, object detection, tracking, segmentation, etc. Pose estimation. Let's have a quick look. Super resolution is very famous. So basically, one of the difficulty that we see in rendering with always a device with always more pixels is to render all of those pixels. It's a tremendous cost. So one way is to render less pixel and try to extrapolate the result. There's traditional algorithms that do that pretty well. However, lately, some technique based on deep learning have showed that they can actually be better than those more traditional techniques. NVIDIA DLSS is one of them. And looking in the future, I think there's a good chance those deep learning based technique will actually address those the huge amount of pixel that we will get on screen. So that's one example. Style transfer is another one, and we will have a deeper look at it because the demo we'll look at the end of this presentation is actually about style transfer. But basically, very shortly, what is style transfer? So you get an image. Could be render, could be picture, and there's two things in that image. As human, we can see the content, which is more likely to be close to the shapes. So for example, on the left, you can definitely probably see that it's some kind of human or a shape that look like a human, even if the style is quite different. So on one hand, you get the content of the image, and on the other hand, you get the shape of you get the style of the image. And style transfer is about keeping the content but replacing the style by another one. For example, on the left here, it's actually a character from the Adam demo from Unity, and Jeremy Cole, which is a MLGFX lead at Unity, applied a style, I forgot the name, a Ferrofluid style on it, and that's quite awesome. On the right, you can see the Viking village, which is also a scene from Unity with 5 different styles. Why is it good? It's good because you can have a different art direction at a fraction of the cost that would have cost the production to reach that point if you will be to regenerate all of the assets. XR object detection, tracking, segmentation. Plenty of use cases. A lot of them are very mobile, because then you get a camera. A note about that: when you're on mobile, you're on a low power device, and it probably means performance is going to be a challenge. So here you can see a network that do face detection, try to predict the age. By the way, those two gentlemen on the left is our Reynald Ziomas, and on the right Modest Pidas, both former creator of Barracuda and a lead of Barracuda. XR pose estimation. So another example could be really useful in augmented reality. But that's not all. So we spoke of real-time. Real-time meaning inference, but during the game, or whatever application it is actually. But what about authoring time? It's also really, really important. And actually, maybe there's even more use cases there. Texture upscaling could be very, very nice. And it's not completely only at authoring time. What about at loading time? You actually take the embedding, some embedding, which is highly compressed version of a texture, and compress it. Could be very good. Smart authoring, two pictures on the right. It will be you try to set up an environment, and AI will help you. It will provide some nice environment. So maybe put the window where human will have put the window because you get a good lighting. Things like that. You will have learn what human find is actually nice. Okay. Let's move to the Barracuda pipeline. So we have seen some use cases, and I hope it shows how powerful machine learning could be for real-time 3D application, both inference time or runtime and authoring time. But now we want those models to actually go from the Python world to the on-device world, and that's what Barracuda is doing. So the flow is from the left to the right. On the left, you get Keras, PyTorch, TensorFlow, any pipeline really. The way it works is that from those library, you will export a non-X file. So most, if not all, of those major library have a simple way to export to ONIX. What is ONIX? It's a format maintained by Microsoft that actually it's some kind of way to serialize a neural network model that everyone understands. All of this pipeline can export to the same format, and that makes it really useful. It's a very well maintained format on top of that. So you export from those library to ONIX. I won't dive into that, but for some of those library, it's actually a one-liner. It's really easy. Then you take that ONIX file and drop it into the Unity editor. What the Unity editor will do, it will convert that ONIX file to our own format, and then with a few lines of code, you will be able to run your model on the device. So let's dive a little bit. On the left, library of choice, convert to Onyx. In the editor, so when you actually drop the file, we process the importing step and convert to Barracuda intermediate representation. At that point, we have the first optimization step. It's the offline optimization. We'll speak about it in the optimization part of that talk. Then after that, you will create what we call a worker. It's some instance of the engine, if I can say so, that will be able to take that intermediate representation, that model Barracuda style, and actually run it. And how does it actually run it? It runs it on a backend. And a backend is the name we gave to the way to run a given model. And it could be CPU, GPU, or maybe something else. So on the top, we can see Unity Burst HPC sharp. So what does it mean? Burst is a compiler, and it compiles a subset of C# to super highly optimized native code. And that's great. That's great because you actually goes from easy-ish C# and goes all the ways to SSE, AVX, Neon, sim-defined code, native code. And on top of that, there's the ability to jobify it. So basically from C# you get highly optimized CPU code. So that's your CPU backend. Then if you want to run on GPU, then we will use a Unity Compute. Unity Compute is the Unity compute shading language, and it's cross-compiled to every platform that support compute for Unity, using JXL, GLSL, Metals, PFE, etc. So there's a little box below, DirectML, and this is to signify that it's not limited to those two backends. Actually, we have a new backend in the work, which is the pixel shader worker. That's allowed to run if you run, for example, on WebGL, where you don't have compute support, but you still want to run on GPU. But what if you want to use NPU, CoreML, NNAPI, DirectML, etc.? Then you could have another backend. And we have successfully experimented with all of those different dedicated hardware, but we don't ship them at the moment. A note about DirectML. So DirectML need to have DirectX 12 as an API. And according to our stats, DX11 is insanely popular still for game developer. We'll see how it goes in the future. It might change. Okay, so optimization. Now we have a model, and that model was dropped into the editor, and we will first optimize it offline. Then after that, once you get a model that's as quick as possible in terms of its architecture, then we will want to run it as fast as possible on the given device, because every device is different. Let's look at offline optimization first. This is not a real model, just a toy model as an example. It doesn't do anything. Let's see what we can do with this model. Let's say you import this thing in Unity using Barracuda. So we will first look at the constant. On the right, you get a matrix multiplication layer from the network, but both input are constant. So there's no reason to run that at runtime. So we compute it at import time and store it. Then here you get two matrix multiplication, one after the other. Those are two linear operations that can be combined. So we can basically save cost of running those two and run only one by adjusting the weights. We do that. Here, it's a little bit of a different example. You get a convolution, which is super IO intensive, and you get a ReLU, which is absolutely not IO intensive, but still need the bandwidth. So if we fold the ReLUs, basically if we do in the same operation, the same kernel, the ReLU at the end of the convolution, then we will save that bandwidth. So we do that. And that's a bit more tricky thing. Depending on your input channel order, what I mean by channel order is it depends of, for example, if you have a tensor which is 4-dimension and your channel, meaning if it's a texture of a color, will be at the end in the memory layout or interleave. Then you might need to have transposes in there. And we can detect if you have a transpose at the top, a transpose at the end, and we actually support the transpose memory representation inside of a network. We can remove the transpose, so we do that. So that's the end network. That's the network where offline optimization have been applied. So it seems much better, right? And that's the funny thing. Sometimes it is, sometimes not. So those are some network that have been optimized offline and then profiled. And you can see the gain. On the right, mobile net, 26% gain. It's awesome. On the left, efficient net, around 1%. It's almost not worth it. So why? Why does it happen? It happens because it depends what is inside your network. Most of the network latency is due to the expensive operations such as convolution, matrix multiplication, which are also called dense. So let's say you have a network which do a gigantic convolution, which take 99% of the time. Even if you do offline optimization and can remove everything else, still gonna have 99% of that time. That is definitely something you could only optimize online. So it really depends on the network. For example, two network on the right, mobile net. Mobile net get this version of mobile net gets 68 layer, and 54 of those layers are actually convolution or depth-wise convolution, which mean in the end 96% of the time is using those convolution. That's really interesting because probably the optimization here will be about online optimization of those convolution. And actually what you want to optimize here is almost only convolution. But ShuffleNet on the left, it's a much larger network. This version have a 182 network layer, sorry, and 56 convolution. And we can see it's a bit more of a shared responsibility for performance. Still a lot of convolution, but you can also get transposition, pooling, add, straddle slice, etc. So when you optimize for MobileNet, you can basically put once you go to online optimization, you can put all of your effort into convolution. For ShuffleNet, it's not like that. You want a lot of effort into convolution, but transpose, pool, add, everything else needs also to be fast. So basically, that's the short story. You need everything to be fast, but convolution, dense, matmul to be extremely fast. Optimization online. So obviously CPU optimization and GPU optimization are going to be wildly different. Let's look a little bit about CPU. So there's various algorithms for convolution in terms of the way to approach a problem. We use a variation of the im2call algorithm. And something that we wanted to highlight here is that it's not only about performance once you are on the edge. It's also about memory. You will live in an application that consumes memory for other purpose, and the device itself have a strong memory constraint. So you want an algorithm that's not only fast, but also have very good peak memory usage. And that's very great we have. And because source is open, and because we deliver Unity as a package, you can check the source. So we spoke a little bit about Burst, the C# compiler, and that's an example of what Burst is able to produce from a subset of C#. We can definitely see SSC intrinsic here, and that's great. We get a good performance boost. I mean, it's a world of difference if you have burst or if you don't. GPU. GPU are awesome because of their raw power. However, it's not one GPU out there. It's a ton of different architecture, and every GPU is different. Which means we also need to have a lot of implementation, because one implementation that will be good for a given GPU might not be good for another one. And actually, it's even more than that. Depending on we're speaking of convolution, depending on the convolution, you might have a different implementation because the kernel is 3.3, the kernel is 5.5, the number of channels as input, the padding, a lot of things. So about implementation on GPU, it's a lot of different implementation. To highlight a bunch of things that differentiate one GPU to another: on-chip memory versus DDR. So some mobile don't have on-chip memory, and it's probably not a good idea to use it in that case because you might end up crashing the cache. A scalar register, some mobile don't have them, which means if you actually rely on that to reduce your register pressure, it's not going to happen. Also, depending, for example, NVIDIA versus AMD, the on-chip memory bandwidth versus the actual flaps, the ratio is different, which means your algorithm needs to be different if you want to get as high as possible in terms of performance. And etc. The number of threads to saturate your GPU based on your input. Basically, a ton of implementation need to be carefully crafted. And yes, again, you can see the source. So what else? What else can we do about performance? We have memory layout. Every performance-bound application is definitely interested into memory layout, and we are no stranger to that. Two different memory layout there. There's more option. We spoke a little bit about channel first, channel last, and that's a visualization of what does it mean. So on the left, we can see two different acronyms. When it's, for example, on the bottom, NHWC, it means channel is the thing which is the closest, which is contiguous in memory. So we can see the color are contiguous. But if the channel are actually the second item on that rank 4 tensor, then what is contiguous is W. And that have performance implication. The funny thing is that some library export in one mode, some library export in another. Yeah, and it's actually, it have an impact both on the online implementation of your operator as well as the architecture of the model itself. What we do in Barracuda is we always import from Onyx, which is channel first, to Barracuda, which is actually channel last. But we have an option to change the internal memory layout. So, for example, on dedicated GPU, you will probably, depend on the model, but you would probably have interest in running channel first. So you can just switch that flag, and internally we will swap the memory for maybe a better performance. Okay, let's move to a practical example. I think I'm gonna go fast on this one. Okay, so the goal was to take an awesome research by the Unity Lab team, and make it runtime on device. It was runtime, but lower resolution on stronger hardware. We took a look at the model, which was using, for example, on the left you can see residual 48. That means that the number of channels in the convolution was 48, which was not a good fit to our implementation of the convolution. So there was one thing where we could improve. Also, importing, we can see activation were taking a lot of time. They should not broadcast. So we basically had a plan, a direction to optimize. But we also knew that it will be still very difficult to get the performance we wanted at 30 FPS. So we look at reducing the input size, and it actually didn't work. because we wanted something very detailed, and doing that will result in very blurry detail. I'm going fast here. In short, there's two very important things I think that could be easily overlooked. Is that in the Python world, you train using some library that will load your texture, serialize them, etc. But once you go into the real-time 3D world, the actual color space is very important. So you might need to check your Python code twice, because the way you train your model will have a huge impact on the final result in game or in your real-time 3D application. In general, training a network is very expensive, so you might want to try to iterate as much as possible, find everything you need to do, and in the end, retrain. So it's interesting to think about how can you continue your experiment without retraining. In the end, we had this result. So we changed the network, run much faster. I'm just going super fast now. And almost the same repartition of speed in terms of profiling, but actually something like 10 times faster. If you Google real-time Unity style transfer, you can find the full video and more explanation about it. It also runs on a PS4, and for that we use a temporal reproduction using tiling. So the network will run on a part of a frame, and then we recompose that using a reproduction and the depth buffer. And that's it. So thanks for listening, and I hope machine learning and real-time 3D will come together and do great things. This is the team. Milan, I think you're muted.
So this is time for me to repeat myself. Thank you for this great presentation. This is very honor to see it from the source. So we have a couple of questions if you're interested for Q&A. So Bruno asked us, can you tell me, can AI be used for automated level generation for virtual production in games, especially in Unity?
So, yeah, definitely. I think it's a broad question, but definitely it can be. There's actually when we spoke of the different use cases, one of them was in that direction, where doing a level generation, a part is very manual, where you actually set up your level and you want to give a specific feel and mood. And yeah, it can do that. Maybe it can add detail. Maybe it can, or the contrary, maybe depend what you want to train it with. Maybe it do the blocking or like the basic layout, and then you do the detail, or the opposite, or maybe it help you with both. Actually, there's tool out there to both of these use cases.
Yeah, maybe then in mix, like if you train it on a certain mood or photograph and give it the base of the assets, which combines elements from the image, maybe in the near future, we can actually generate an entire level out of photograph, maybe also generated through style transfer. So also in that manner, I wanted to ask you something. In your opinion, how does style transfer reflect on game art direction and aesthetics?
So I think it's a bit of a challenge, and that's still a very researchy subject, I suppose. The reason is because style transfer so far, if you look at if you Google style transfer, you're gonna find a lot of paintings. But one of the feedback that was, I think, really interesting when we work on that style transfer demo was that one of the artists say, I love it, but it's kind of removing detail. What I want is the contrary, because it's very costly to actually create the detail. So give me a tool where I will do the rough, the easy work basically, and then it will provide all of those details. And at the moment, I think style transfer is much more into some kind of impressionist painting maybe. So it's more dreamy detail. So I think there's research in that area that should happen. So style transfer could be used in the way the artist want it. So if you go toward very painting, dreamy, artistic direction, there's probably use case now. But if you go to another type of artistic direction, I think we're still It's still not there.
Yeah, still not there, but I really like the term that you used in your presentation that the models were hallucinating. Maybe we get a new art direction in games like, yeah, like make it like hallucinated, and we get the whole genre of real-time applications.
Mhm.
So we do not have enough questions. Is there maybe anything else that you would like to add on a topic, or select? What would you like to add?
Um, po- 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 po. Top of my head, no.
Yeah.
Uh,
Okay, so but this is yeah, enough already, in terms of information, and we will maybe let our audience, to slow his pace down because we really got many useful stuff from you. Thank you very much for your exciting presentation and sharing your work and research with us, and looking forward to speaking you in the future. Thank you very much.
Thanks, Milan.
So, thanks everyone for joining in to Florent's presentation. I hope you see the opportunities for your technical, artistic, and general real-time applications of machine learning in real-time applications, game design, or anything else. If 2020 showed us anything, it is that virtual productions are the next new thing. So tune for your next presentations, and thanks CGA for having me. Bye.